Welcome to the Wi-Fi Alliance webinar on testing of the 6 GHz standard power devices. My name is Alex Roytblat. I am with Wi-Fi Alliance, and I will lead today's discussion. We have over 450 participants registered for this webinar, so the level of interest is really encouraging, and everyone is welcome. As many of you know, a little over 3 years ago, the US FCC adopted the decision to open 6 GHz band for license-exempt technologies, such as Wi-Fi. This momentous decision unleashed a wave of innovation and inspired corresponding regulatory actions in dozens of countries around the world. One important element of the FCC's decision is to allow operations of the standard power devices under the control of the Automated Frequency Coordination System, or AFC. Wi-Fi devices operating at standard power levels have an increased performance in terms of connectivity and coverage, and therefore are critically important to the rapidly evolving 6 GHz Wi-Fi use cases and ecosystem. And that is why Wi-Fi Alliance members have dedicated time and resources to advance development of the specifications that we will share with you today. Over 200 Wi-Fi Alliance members from over 80 companies, along with Wi-Fi Alliance staff, labored cooperatively for several months to produce this specification framework, which will enable FCC, as well as regulators in other countries, to ensure compliance with the applicable regulatory regimes. And this framework is essential to ensure compatibility and interoperability of the standard power devices. As many of you know, a few months back, jointly with Winform, Wi-Fi Alliance held a similar webinar to present specifications for the AFC system. Today, I'm proud to share with you the other half of this milestone achievement, namely the specifications package for the 6 GHz standard power devices. I will not take up more time with introductory remarks, and I will turn it over to our team of experts that we have assembled for you on details. And I will only mention a few things. First, please use the comment tab to post your questions on the platform, and we will do our best to answer them as time allows. If there is time at the end of the sessions, we'll try to answer them then. And we also allocated some time for Q&A at the end of the webinar. Second point, all the materials that we will present today, along with the webinar video, will be publicly available on Wi-Fi Alliance website. We encourage you to review it and share it with your colleagues and within your organizations. So with that, let me take you to the agenda for today. And as you can see, we have assembled a group of experts, starting with Thomas Derham from Broadcom, and he will cover the AFC system to AFC device interface. Then we'll go to the AFC DUT compliance test plan, which will be presented by Tevfik Yucek from Qualcomm. Then Stewart Strickland from HPE will present the AFC DUT compliance test vectors. And then Lakshmi Nakaraya from Wi-Fi Alliance will present AFC DUT Harness and AFC DUT testing for FCC specifications. And then we'll also share the next steps and go to the Q&A. So with that, I will take you to, again, a reminder that please submit your questions through the comments tab. And with that, I will take you to our first presentation, which is, again, as I said, by Thomas Derham on AFC to device interface specification. So Thomas, please take it away.
Yeah, great. Thank you, Alex. Hello, everyone. So yeah, my name is Thomas Derham. I'm a Wi-Fi standards engineer at Broadcom. I'm active both in IEEE, where I worked on the 6 gig design in 11AX and 11BE, and also in Wi-Fi Alliance. I work on a number of programs, including Wi-Fi 6E, Wi-Fi 7, and the 6 gig AFC. So my presentation today is a kind of brief introduction to the Wi-Fi Alliance's AFC system to AFC device interface specification. The idea to set the scene for the subsequent presentations on the compliance testing. So this slide just shows where this interface is actually used. So the specification document defines the transport, the signaling, and the behavioral requirements for this interface that's between the AFC system at the top of the figure and AFC devices. So it's basically the blue lines that you see there. The AFC devices are either standalone APs that make a direct connection to an AFC system, or a proxy that's acting on behalf of some non-standalone APs, or of course a fixed client device. This slide just talks about the transport and security aspects of the interface. So it's a fairly straightforward API based on HTTPS. So there's post-based request and response. The request includes the information about the location, registration information, and so on. We'll show in the details at the minute. There is a URL for the AFC system and its endpoint. So an example is shown on the screen there. And then the response comes back from the AFC system with the allowed channels and power levels. So this is HTTPS, so it's based on TLS security, version 1.2 or higher. And that TLS establishment before any exchanges take place include what we call service certificate validation. So this is where the AFC device, for example, the AP, is validating that it trusts the AFC system server that it's talking to, based on the URL and root certificate, which are configured as a trust basis on the AFC devices. The device needs to do a number of things to perform that validation. So it checks the server certificate itself with a matching against the host name and the URL, validating the certificate chain to the configured root certificate, and also checking the revocation status of the certificate as well. And if any of those fail, then it doesn't connect. And so the purpose of that is to make sure that the device never inadvertently connects to, in inverted commas, rogue AFC servers. And the TLS ciphers also ensure the strong encryption and integrity protection for that link. The payload that is sent in the request and response is JSON-based. So there's a number of mandatory fields that we'll discuss in a moment, plus some additional fields that can be used for vendor-specific extensions. This slide shows the request object. So we've got this available spectrum inquiry request there. There is a device descriptor field, which basically includes all of the registration parameters for the AP. Those are actually embedded in every single request. So registration is kind of implicit within, if you like, the first request which is made. There's a device descriptor object there that contains a serial number, and then certification ID object, which contains an array of rule set IDs. So for example, ones corresponding to FCC Part 15 rules, and also an ID, so an NRA ID, such as FCC ID. And then we'll talk in a moment about the location object that's just below that, which contains the geolocation of the AP. And then there's a couple of objects which describe the nature of the request that's being made in terms of the frequency and channel ranges. So the channel-based request links to the channelization that Wi-Fi 802.11 uses, so-called operating classes and channel numbers, and/or a request could be made for a frequency-based mask and with specified frequency ranges. This slide goes into a little more detail about the geolocation object, which is included in that request. So there's three different kind of geometric alternatives to how the the location of the AP is described in terms of horizontal geolocation and uncertainty. There's an ellipse, a linear polygon, or a radial polygon. So you can see there that there's a Latin long coordinates, and then there's effectively an uncertainty radius in the horizontal domain, defined as the major and minor axis in case it's not circular. And then there's a separate part for the altitude, so the vertical geolocation, either AGL or AMSL elevation, and that also has its own vertical uncertainty value associated with it. And those uncertainty values, of course, are required to need to are defined such that they meet the 95th percentile requirements for as FCC require. There's also an indoor flag there at the bottom, which can be used if the AP is indoors and the NRA allows use of indoor for the basis of the power calculation, such as taking into account Bell, that kind of thing, then that field can be used for that purpose. The next slide shows the response object. So we have this available spectrum inquiry response object, which is shown here. So again, this is kind of linked to the request in terms of the request ID, and then and the rule set ID that was used to calculate these channels and frequencies. And then depending on whether the request was for a list of channels or frequency range or both, there's one or both of these objects, the available frequency info and the available channel info. The available frequency info object essentially shows a list of PSD limits for each frequency. So the PSD on a per megahertz basis over the frequency range that was requested. The available channel info object shows a list of operating classes and channels within each operating class. And then for each one of those channels, so operating classes are basically different channel bandwidths, 2040, 80, 160, and so on. Then for each of those channels, there is a maximum EIRP, which is defined. And that also takes into account the adjacent channel requirements and so on for operation on that particular channel. And then finally, there's a response code, which hopefully is going to be success. But if there was some error with the request or the ability to calculate the responses, there's also a number of error codes defined. And then so once the AP then receives that response, then it needs to use it in terms of the channel and then the power selection algorithms that it's that it's using if it's operating in a standard power mode to make sure that it's compliant with that response. So basically, for a channel-based response, it needs to use an EIRP on a given channel that doesn't exceed the specified EIRP limit in that available channel info object. For the frequency-based response, it needs to fit essentially its entire transmissions, including adjacent and so on, within the PSD mask that it obtains within that frequency object. And then the last slide here is about support for proxies. So as we showed on the first slide at the beginning, a proxy is one of the devices that can interact with an AFC system. For some reason, the figure here is slightly moved on the screen. But the message structure allows the request and response messages to be sent, including multiple requests and responses within them. And each of those can correspond to a different non-standalone AP that's under a proxy's control. So they can be kind of batched up. And then the AFC system will process those as a batch and provide the response for that entire batch. Each of those requests is going to be for a separate access point with its own serial number, in principle its own geolocation, and so on. In some cases, the uncertainty could account for a kind of batch of APs that way. And as far as the security is concerned, that's going to be established between the proxy and the AFC system. And then the way that the proxy then provides those responses back to the individual APs and ensures those APs are compliant is not defined here. That's assumed that it's going to be handled by the vendors as part of a complete system. And that is it on the specification. So I don't know if there's any questions. Otherwise, we can hand over to the next part.
I'm not seeing questions in the comments section, but I had a question just on the issue that's near and dear to my heart, which is the indoor flag. And can you elaborate on how exactly the device will set that flag in communicating with the AFC?
Mm-hmm. So I guess that this field is left open in the sense that how it can be used, I guess, is going to depend on the regulatory rules. So if an AP is installed indoors, in principle, it can set that field to 1. That might be based on whether or not it is, also certified for an operational mode which ensures that it's indoors, or it could be a device which potentially is professionally installed indoors, or whatever it may be, that can be set, and then the AFC system, obviously in compliance with the regulatory rules, could use that accordingly.
Okay, thanks for that. I see that some folks are commenting that they just recently joined. So I'm not sure if we'll get the questions in the chat or the chat is just populating. But in the interest of time, let's move forward. And then if there are questions, we can come back to make sure that we answer the questions that come up. So with that, let's move to the next section of the webinar, which is on AFC DUT compliance test plan. And Tevfik Yucek from Qualcomm will present that. So thank you, Tevfik, and please proceed.
Thank you, Alex. Yeah, my name is Tevfik Yucek. I work for Qualcomm. So Wi-Fi Alliance has developed this DUT compliance test plan, and the test plan provides a methodology to verify that standard power devices conform to AFC-related requirements by regulatory bodies such as FCC. So when you have an access point, that access point is a standard power AP, needs to meet certain requirements. And one of them, unique to the standard power, is they should be able to communicate with an authenticated AFC system, understand and follow the instructions from the AFC system. The test plan covers standard power access points, fixed client devices, and proxy components. These three, in general, is called as standard power devices. In the test plan, we cover both channel-based and frequency-based inquiry requests. As Thomas mentioned, the inquiries could be, the response from AFC system could be for each channel, Wi-Fi channel, or it could be just a frequency range, and it gives AFC system gives the frequency response as a power spectral density for each megahertz. So AFC test harness has the test plan has this capability to test both options. Also, there will be certain devices that are known as composite devices. These devices can operate as LPI, low power indoor devices, only indoors, as well as they support standard power operation. So the test plan could cover such devices, because sometimes they might not have a successful AFC inquiry. However, they might still operate as LPI, and they might test. So that kind of devices are also covered in the compliance test plan. The test plan does not cover certain aspects. The first one is RF emissions requirements. This is like maximum power, maximum bandwidth, out of band emission, spectral mask. These are covered as part of regular device certification. So they are not really specific to standard power operation. They are not covered. The geolocation requirements for standard power devices is also not covered. That includes automatic determination and verification of accuracy and uncertainty of geolocation. Finally, the test plan does not test for the requirements of standard power devices for daily contact of the AFC system. Actually, this slide says some aspects of security of the connection is not covered, but we'll talk about that, and there's a good coverage for the security. So this is a summary of the tests that we run as part of the compliance test plan. There are 5 categories: successful registration and spectrum access. So this is, I'll talk about them in detail. Basically, an AP, standard power device, could send an inquiry, receive the channel response, and then act on it and start transmitting. The second test is USA, that's unsuccessful spectrum access. The device sends an inquiry, but it doesn't receive any channels. We need to make sure that device doesn't transmit. That's the second part. And then the next two are really spectrum updates. So device has done this, and it's operating as a standard power device, and then it needs to send another request and get a response. Maybe a 24-hour has passed, and then we verify that the device still honors this response from AFC system during the update. Finally, the last part is about server validation. This is part of the security. This is to prevent a standard power device accessing to an unauthorized, unapproved AFC system by FCC. I briefly mentioned the details of these tests. I will just explain some of the nuances, but in the DUT test plan or in the slides, there's more details. Because of the time, I'm not going to read through all of the slides here. First of all, test harness validates that all the information, mandatory information fields from the available spectrum inquiry request is available and properly populated by the standard power device. That in all of the tests, we do this. In the successful registration and spectrum access test, a list of available frequencies and the maximum permissible power in each of these are provided to a standard power device. So again, everything is as expected. Device sends an inquiry, gets a list of channels and power levels. Now, the test equipment monitors to determine that device does not exceed the LPI limit for DUT, for devices whose manufacturer attested to its compliance with rules for LPI operation. So the first test is, if this device supports LPI operation, its power should not go beyond the LPI power limit. Second check is it does not begin transmission in the band for standard power on the operation prior to AFC authorization. And also any subsequent transmissions conform to the conditions of available spectrum inquiry response. So let me give you an example, to understand this. I think that might help. So AFC standard power, AFC test harness might say, okay, only in this channel you can operate at 36 dBm. Then we check. We need to make sure that that device does not operate at that power level before the authorization. If it is standard power only device, it should never transmit in the 6 GHz band. And if it is a composite device that supports LPI, it might transmit at 30 dBm, which is the LPI power level first, but it should not go to 36 before it receives this response from AFC system. The unsuccessful spectrum access request is similar, but in this case, no frequencies are made available to the device. So in this case, we make sure that if the device is standard power only, it does not transmit in the band, because AFC told the device there is no frequencies, there's no channels available. And for a device that is LPI capable, the transmission should not be above LPI limits. The third test here is a successful spectrum access update. In this one, you have a device which has completed the AFC inquiry and started operating in the channel, and now it sends an update, another request. And the test harness responds with response containing significantly different lists. Maybe previously you could operate in the lower part of the band, but now AFC system is telling you can operate only in the upper part. Then we, just like the successful spectrum request test, we validate that the device is indeed honoring this new request, and then it is moving its channel to this new channel. Similarly, if the device supports LPI, through the RF test monitoring, we verify that, in the new frequency range, outside the frequency range that's provided, it does not go beyond the LPI power level. And if it is a standard power only device, it should only operate at the power level and frequency ranges provided by the update. I think you see a trend now. This one, in the update, unsuccessful spectrum access update, AFC system basically says there is no frequencies available for you to use. And then through the RF test equipment, we verify that device, if it supports LPI, it does not go beyond LPI power levels. And if it is a standard power only device, it should not transmit, because in the update, even though previously it might have given channel availability, in the update, we know that no frequencies are available, so it should not transmit. That's what the test validates here. Okay, the last test is unsuccessful server validation. This validates that AFC DUT correctly performs server certificate validation and refrains from sending a spectrum access request to an AFC system if validation fails. As per regulatory requirements, a device needs to know that it is communicating with an authorized certified AFC system, and that's achieved through server certificates. And in these tests, we make sure that if there is something wrong in that server certificate, device should not try to communicate. And different aspects of server certificates are tested here. Again, we need to make sure that a device that will be operating as a standard power device needs to be communicating with an authorized AFC system. And there are different ways to break this authorization. You can read through tests 1 through 8 here. And then finally, we install a correct root certificate and then make sure that device could still communicate with the AFC system with the correct URL. That concludes my presentation. I think we could have a couple of minutes. Alex?
Yes, thank you, Tevfik. Or perhaps it is on the test plan. So how does AFC take into account the propagation losses for the device and the antenna gain and such? So how does the device communicate all that to the AFC, and how is it tested for?
At this time, at least in the countries that allows AFC operation, we cannot take the standard power devices antenna gain or directionality into calculations. So AFC system will respond with the same channel availability to any device that is requesting. So there is no way for a standard power device to send that information to the AFC system. Similarly, the propagation loss, it is determined by the AFC system. AFC systems, will have to get their own certification. So that's really beyond the scope of this discussion. The focus here is really standard power devices or device under test. Think about it like the access point, it sends its location, AFC system does the calculations based on its certification and returns the channel availability. The device, the access point, your access point doesn't have any say on what propagation models should be used. Of course, AFC system knows its location and it checks whether it's in an urban area, can I apply clutter, all that details. But they are again beyond the scope of this discussion. That's really on the AFC system side.
All right, we have time for one more question, and I think this is a good one. So is there a test bed or a setup that where this test plan is implemented, or how do you envision this this test plan being used by regulators as well as the equipment designers and developers?
Absolutely. Actually, the answer is yes, and there will be a presentation today, and actually there will be a demo of Wi-Fi Alliance developed test harness, and Lakshmi is going to talk about that, and also the test that Wi-Fi Alliance has done, and who's going to do this test. I think we could defer that question to Lakshmi's presentation.
All right, very good. We're right on time, so let's go to our next section, which is on AFC DUT compliance test vectors. And Stewart Strickland from HP will cover that. So Stewart, please take it.
I'm Stewart Strickland. I'm wireless CTO at Hewlett Packard Enterprise. I'm also the chair of the test vector specialist team within the AFC task group and a vice chair of the AFC task group at the Wi-Fi Alliance. And I've also participated actively in the WIN forum on this topic. I'm going to share with you today an outline of the test vectors, which are essentially the instantiation that Tevfik just spoke about, the interface specification that Thomas introduced you to earlier. This will be a relatively brief part of the presentation because I think the substance of what we're trying to do here was really conveyed by Tevfik, and the mechanics of it will be presented in detail by Lakshmi in just a moment. But I did want to give you a sense of what the vectors are trying to accomplish. So essentially what they are is a pair of requests and responses. The requests will come from the system under test. So it will need to be provoked by the harness to make a request of a dummy AFC system, which is essentially the test harness, for spectrum availability. The system under test, the device, the essentially access point, will receive a response from the test harness, a response that mimics the response it would have gotten from an AFC system. And that response will contain of available channels or an array of available frequency ranges and the power levels that correspond to each maximum allowable. The test vectors are designed to give the DUT, give the device under test instructions, and all that we're really looking at is does the DUT do what it's told? If told that certain frequencies or channels are available, does it conform in its subsequent behavior to the instructions it received from the AFC system, or does it deviate? If it conforms, it passes the test. If it deviates in a way that either transmits outside of the range that the AFC system, or in this case, test harness, has told it is available, or transmits at a higher level than it was told that it's available, then it will fail the test. And this is monitored, as Tevfik told you, by RF measurement equipment that is monitoring the transmissions of the DUT, and it's really pretty straightforward. I will say that there's no necessary link between the content of the requests that are in the test vectors and the responses. The device under test is provoked to make a request because we got to get the system going, and but the responses that it gets aren't not necessarily for a real geographic area, for a real availability at any particular place in time. What's important is just that we convey to the some instructions and then make sure that whatever instructions it gets, it follows. So that's essentially the philosophy of what we're doing. And in terms of coverage, the test vectors, there's a set of test vectors for each of the test cases in the test plan that Tevfik outlined. And for each of those, the system will declare whether it wants to be tested for inquiries based on frequency, inquiries based on, or whether it's capable of making inquiries based on both channels and frequencies, and then it will be provoked to enter the tree of test vectors in a way that's consistent with that for registration and the access requests. There's a set of ways in which this can fail, that no spectrum available, and there's a group where having previously received availability, a new availability list becomes available, and making sure that the device is not still following the old availability list. And then finally there's a series of tests in which, for one reason or another, the attempt to validate the server connection fails, and no availability is reported back to the device under test, and we make sure in that case that the device does not transmit. I would say that in none of these cases are these test vectors aiming to validate. They're not a protocol test. They're not aiming to validate that the requests are well formed or consistent. We're also not testing the accuracy of the location that's being reported. We're just testing that whatever the AFC device is told by the surrogate for the AFC system, it follows those instructions and it doesn't do anything else. So I think that's probably as much as one can say about the test vectors themselves. I hope that it will become clear exactly how they are used when Lakshmi presents the explanation and demonstration of the test harness. So Alex, back over to you for questions.
Right. Thank you, Stewart. We do have time for a few questions. Some of the questions that I'm seeing are concerning the location capability and testing for that. So you mentioned that the geographic area doesn't factor in, so the test vectors are not geographic area specific.
So in creating, this is more broad in its scope than just the test vectors, but in creating the test plan, we did not set out in these tests to test the capabilities of the device to locate itself. It is required by FCC rules to be able to automatically locate itself with 95% confidence. And there will be compliance tests for the devices, FCC tests in this case, that it can in fact do that, or maybe those will be done by declaration. But we don't assume that there is any satellite signal in the lab, or that the location that's being reported is the actual location. That wouldn't even actually make sense in the case of these tests. So there's no test of the DUT location involved in these, and there's no correspondence between the channels that it's told are available and the location that it reports in its request.
All right. Thanks, Stewart. And as far as testing for indoor versus outdoor, are the test vectors taking that into account, or not?
So it's not really relevant in the protocol. Of course, the device can declare whether it is or outdoors, and the AFC system test cases, the AFC system could take that into account. But here, given the device has just been given a range of frequencies or channels that are available and power levels, and all we're testing is that it conforms to those. Whether or not those were calculated based on statement of being indoors or outdoors isn't really relevant to whether or not the device is actually indoors or outdoors.
All right. And so another question is, when the AFC approach expands beyond US to other regulatory jurisdictions, are there plans to develop test vectors that will support operations, let's say in Canada or elsewhere?
So the protocol, the test plan, and the test vectors are all designed to be extensible to cover other regulatory domains. Initially, because these requirements were available, all three of those documents were based upon the FCC requirements, but it was envisioned that there would be updates of those documents or appendices or supplements that would cover additional or different requirements for different regulatory domains. Hopefully, they will remain, relatively within the same framework so that the extensions forward. But yes, the plan is if there are new requirements, say from Canada or from another regulatory domain, that appropriate test vectors would be issued for those.
All right. All right. Thank you, Stewart. We are a little bit ahead of time, but I'm thinking it would be most valuable to hear from Lakshmi on the test harness, and then we'll have a complete picture of the specifications and leave more time for Q&A at the end of the webinar. So with that, let's go to Lakshmi Narayana on the AFC DUT Test Harness. Lakshmi, please take it away.
Thank you, Alex. Yeah, my name is Lakshmi Narayana Mukkapati. I'm Director of the Systems and SQ Engineering at Wi-Fi Alliance. Been with Wi-Fi Alliance for several years and recently supporting AFC efforts from the staff working with the AFC task group. So with that, let's get into the AFC DUT Test Harness topic. So before we get into the details, I would like to just, introduce some of the definitions that we will be referring as part of the AFC DUT Test Harness setup. So as you already familiar with the previous speakers covering the AFC DUT, so this is including the 6 GHz standard power AP devices, fixed client, or a proxy representing one or more non-standalone standard power APs. And then AFC DUT Test Harness is an automation utility that is, in a way, acts as like an AFC system, which can provide channels and availability of the ARPs and frequencies and availability of the PSTs, and which follows the Wi-Fi Alliance AFC system to device interface specification. And another piece in this test setup is that RF test equipment, which will be used to analyze and measure the different ERP values at different channel weights being transmitted. Is basically, we also measure when there is no response given by the AFC system or simulator. We ensure that the device does not transmit in a standard power. And then when the request is given and when the device start operating, so we measure in what channels and what power levels the device is being operated. It's for both channels and frequencies. So this is the quick figure of the AFC DUT test setup. And as you see, we have 3 figures here. One is for representing the standalone standard power access point, the top one, where you can see the setup is very compact, or we can say very simple. It's a AFC system, AFC test harness. And then we have a access point, which is we call as AFC DUT system, and then we have RF test equipment. We'll get into more details, but here the AFC test harness controls the test execution, which will basically trigger the DUT to send a request. And the DUT can choose to send the request based on the list of frequencies it supports, list of channels, or it can send both frequencies and channels together. And then the AFC test harness provides the response to the requested frequencies and channels. And then using the RF test equipment, we measure what channels being transmitted, and then what levels are being transmitted by the DUT, and then ensure that those limits are within the limits provided by the AFC system. And coming to the proxy, with the proxy is that can work on behalf of multiple non-standalone APs. So, I mean, the figure we are showing just 2, but it can have multiple device representing multiple devices. So our SDI specification, system to device interface specification, does support receive AFC DUT sending aggregated request, and then system responding to those aggregated requests. So in this case, the APs will forward the information to the proxy, and then proxy aggregates that all those individual requests and send it to the AFC system. and then AFC system would respond back to the frequencies or channels available, PIRP and PST respectively. And then similarly, we use the RF test equipment to measure the maximum permissible power limits for these individual devices. And the third setup is something that fixed client device. This is another type of devices that is allowed to use standard power limits. And this fixed client can operate as or can communicate with the AFC system and directly get its maximum permissible power limits. So in the case of fixed client, as you see, we call the AFC DUT system as AP plus fixed client, because for the fixed client to start even transmitting, it first need to connect to a standard power AP. So that's why it needs to establish a connection or association to a standard power AP, and then it can choose two ways, or maybe there is another way that it can send the request for the frequencies or channels with a maximum permissible limits through the AP, means through the wireless connection, and then AP forwards that request to the system, or in this case test harness, or it can choose if there is a backhaul connection from the fixed client to the AFC test harness, then it can directly forward that request to the AFC test harness and obtain the permissible power limits. So, and again, all this communication follows the Wi-Fi Alliance AFC system to device specification, and which uses also recommends TLS 1.2 or higher versions for establishing the authentication between the AFC DUT and as well as AFC test harness. So now we in a previous slide we have seen how the system, the setup of the AFC DUT looks like, and then now we go into one more level deep on the architecture of the test harness. So as you see on the left side, what we call is the AFC DUT test harness, and the right side is the AFC DUT system. So we have Wi-Fi Alliance has developed the AFC DUT test harness using test framework. And that is where I will introduce in the live demo the UI and then how the execution takes place. So in these components, as you see, the test tool, that's a binary release, but that's mostly used for the UI and test execution. And we also have developed the test modules to support the AFC test harness in a way to work as an AFC system. So those are the modules, as you see, AFC system simulator, which has the functionality to receive the request and then send the pre-populated responses. And then AFC test scripts is something like Tevfik and Stewart mentioned about the AFC DUT test plan and the test vectors. So to complement to test those elements like the test plan and the test vectors, we have developed the test scripts. And then of course the validator is to validate that once the device sends a request and then it gets a response and then it start transmitting. So using the RF test equipment, we measure what are the values being used by the device for the transmission. And then those values being fed to the harness and then harness using the AFC validator module, it would determine whether that is aligning with the mask that is provided by the test harness, and which will be used to determine the pass-fail criteria for an individual test case. So Wi-Fi Alliance also published all these modules as an open source, and they are available on our GitHub, and which we'll go through those links and the information in the following slides. So we also want to talk about this AFC DUT system. So there are several ways of execution being supported. As you see, the AFC DUT system has mainly two functions. One is for the control app, and another one is the AFC function that are specific to the AFC. So the control app is for receiving the commands from the test harness and then responding back to if there is a let's say what channel is being used to transmit. So so it's basically receiving the control commands and respond back to what is being requested by the test harness. And this part is optional to implement. And if a device choose to implement the control app, that will expedite the test run. But there is also we have enabled way to run without implementing the control app. So and Wi-Fi Alliance also developed this control app and made it available as an open source for the standard power device vendors to utilize this control app to be able to do the fully automated testing. And then AFC function is responsible for receiving the request, or even triggering, formulating the inquiry request, and then sending that to the AFC test harness, and then receiving the response that is coming from the AFC test harness, and then acting on the response received from the harness. So now going into the next level, so what are the things that need to be available to do the AFC DUT test harness installation? So the requirements are very minimal, I would say basic. That's you would need a system or a laptop that supports x86 processor and minimum 2 GB storage for running the app, the UI, and saving the logs that are generated from the test run. And then, of course, 8 GB RAM, this for the speed of execution. 8 GB is sufficient, but we would recommend 16 GB, so that faster execution, the system will be faster. And then we are supporting the latest Linux distribution of Ubuntu 22.4.2. And this is a LTS version, and it's available for next 10 years. So I think there would be no issue on supporting availability of this OS version for next 10 years. And then there is we provide a package, Debian package. It's a very simple installation, and just have to issue a single command, and that will install all the prerequisite packages, all the components that are required to install the AFC DUT test harness package. As you see, that's the just a apt install command. And the only thing is required is when you install this package, in order to install the prerequisite package like Python version and other elements. So please connect the system to the internet, and that will take care of everything, installing the package and And once that is installed, this is something I will also show how the user knows that it is installed, and how the user can launch the application. So just go to the activity screen and then search for in the search button, just search for WFA. You would see two screens, the two icons. One is for the launching the application, the one we are showing on the right side with an arrow pointing. And then another one is, let's say, we also support multiple ways of installation when there is a new package. You can uninstall and then do a installation of the new package, or there is a way to upgrade as well. But I think we would, in this version, we recommend to use the uninstaller icon to uninstall, and then you can use the new package to install it again. And it takes, I think, minute or two to do installation, but once installation is done, then app is quick to open the app for the test execution. This is something I was mentioning. So there are a couple of elements or the packages that are here. So as we saw in the DUT architecture, AFC DUT architecture, so we have, this is a GitHub repository where we have open source the modules that were developed for test harness, such as the test scripts, all the test scripts that complementing the Wi-Fi Alliance AFC DUT compliance test plan, test vectors. All those scripts have been available on the GitHub, as well as the validation module and the simulator, which is responsible for sending the responses to the coming request from the DUT. And then, of course, we have the DUT package. So this package is built including all the components that are mentioned. And so if user downloads this package, so we have sometime back we have updated this package, but we have new versions to this package, and we will also provide an update, and when we are planning to provide an updated package. But this is something we have some events, and we have been validating it, and it's a pretty good shape now. Once this package is installed, then user does not have to get anything from the open source. But of course, if user interested to see how it's being done or look at the code, then it can always refer to the open source code available on the GitHub. And then the third element is that all the test plans, test vector documents are available in this Wi-Fi Alliance website, which is the link here. And now going to the test harness. So because there are a lot of requirements on the regulatory and what we want to say what are also being, as you see, with the multiple elements in the test setup. So this is something will be helpful to cover what is being covered in the test harness and what is not being covered in the test harness. So as Thomas pointed out, went over the overview of the Wi-Fi Alliance AFC system to device interface specification. So the test harness does cover that the device is following the SDI specification, meaning it follows the request message, and also, of course, the response coming from the test harness. So it validates that request is containing the mandatory information such as location information, FCC ID, and uncertainty area, those elements that it covers. And if any of those elements are not present, then the test harness would reject the request. Then Wi-Fi Alliance AFC task group also recently approved the SDI specification, which lay out the protocol version as 1.4. So the test harness does check for the protocol version being requested in the DUT is 1.4. And then as also covered in the previous presentation, so the test harness does check for the server authentication by the DUT. So the AFC DUT using the root certificates, it does validate the certificates, server certificates present on the test harness, and then do the authentication. And also it supports the so there are multiple ways of sending a request from the DUT. So and as of it's up to the implementation, meaning the devices can send just a channel-based request, or it can just send frequency-based, or if it supports both, then the device can send an inquiry request for both channel and frequency. And we will see all those in our test harness how being implemented, and the test plan and test vectors does cover all those scenarios. Then, of course, the another piece is that it checks that the device is under the control of AFC system, which means when a harness provides the mask for the DUT based on the inquiry request and response, it's received. So let's say it provides for channel CFI1 EIRP as 25 or 27 or even 30, right? So using the RF test equipment, it does check that okay, and the channel, if the AP is operating that particular channel, we measure and then ensure that it is not going above the limits provided by the AFC test harness or the AFC simulator. And what is out of scope is the RF limits. It's like the maximum limits that the device has to obey to the based on the regulatory limits. That is not something the test harness covers. And then the specification of the RF test equipment, like what all the RF test equipment, we can the test plan does say what needs to be measured. As long as the device measures, the RF test equipment is capable of measuring those ARP and PST values. And of course, for PST, it also needs to measure the adjacent channel, adjacent frequency emissions. But it does not check the specification of the RF test equipment being used for the testing. And of course, with RF test equipment, there is always calibration comes into place. Whenever you do measurements, that equipment has to be calibrated to ensure that there is no incorrect readings are happening. So that is something it is on the users or the labs, whoever using the RF test equipment, to ensure that it's properly calibrated before it's being used for measuring the PSD or ARP values. And another element here is that, as we covered as part of the architecture in the AFC DUT system side, there is 2 elements that we covered: the control app and then the AFC system. So as I mentioned, in the control app is something optional, but if the SPD vendors, standard power device vendors, decided to use the control app or implement the control app, so then Wi-Fi Alliance also has developed a control API specification, which will be published along with the AFC DUT Test Harness package. And it's a very, I would say, very simple and less number of commands that are required to be able to take the full advantage of the automated testing, or even for that, say, increase the test execution efficiency. So as you see in the table, we have sample API messages. So there's just for configure, and configure is like for BSS operation, and then for the operation is to trigger the request, and then get info is for like what is the channel that or frequency that the device is operating, so that it can be fed back to the RF test equipment to do the measurements on those specific channels and the EIRPs. And these are some of the capabilities, and I'll show you more when we are doing the live demo. So the test harness does support a number of test execution modes. So meaning it does support fully automated testing when the RF test equipment supports automation, as well as the DUT supports the control app. So then the user can, the labs can run fully automated execution. In cases of either of them, meaning the AFC DUT or the RF test equipment does not support automation, then our test harness is capable of supporting the semi-automated based on the automation available on the DUT side or RF test equipment. And by the way, our RF test equipment does support, the test harness does support any RF test equipment as long as it is capable of complying to the requirements that are mentioned in the AFC DUT test plan. And then test report, we have, I will also show this test report as part of the demo, but we have a nice HTML report that will list out the test cases and then pass-fail result, and also shows the important aspect is that what we call as a traceability matrix, though associated each regulatory requirement that is being fulfilled in those test vectors are being shown in a summary table. And then, of course, more importantly, we also have a lot of log files being generated. The user can see as part of the live execution, and also in case for whatever reason, if you want to look at those log files later for debugging. So we have a pretty good number of detailed log files that are being saved, and the user can always refer to those log files to analyze what's happening with the test case in case of there are failures. Okay, we will go to the most awaited part of the live demo. So let me share my screen with the setup. I hope you can see something that says a UI with AFC DUT Test Harness on the right side corner. So this is the Wi-Fi Alliance AFC DUT Test Harness. And before I go into the test execution, I will show all the configuration options that are available. And then the one thing that I was mentioning is that when you install the tool, and this is where you go and search for, so you will see these two icons, and the one on the left side is the one you can use to launch the application. And then with that, let me go to the UI, and then we can. So there are two tabs that we have on the harness. As you see, this is the AFC DUT harness, and then you can see the version that is being currently used. And we will update. There are a few other things that we are being worked out, and I'll provide you details later. And we will that you can verify that the version that is being installed. So currently, I'm using 118 is the version, but there may be a few updates coming in later. And so there's two main tabs, settings and test cases. Inside the settings, we have 3 sub tabs, which is a test configuration. So this is for like this is a tool IP, and then you have an option. The user has an option to where you want the logs to be saved. So we have a default path being, but that user can always change the path if you have a preference on path. Then, of course, the DUT, if the DUT supports the automation, then yes, there are 2 types of DUT, access point and station. And I will show you how these are translated to the 6 GHz standard power devices like standard power with proxy, or the fixed client. Then, of course, the DUT IP address and the port number. Right now, you see this is grayed out because I have I wanted to show is the manual mode of the DUT to be more interactive in this session. And then, of course, this is for the vendor information. So the SPD vendor information, the company name, and then model number, which will be shown in the HTML report. And on the test global configuration, this is for allowing the DUTs to do the execution either manual as well as automation. So if the device supports API, then you can say false. And if the device does not support the API for automation testing, you can set it to true. That's what I currently have. And then when we go to the test specific configuration, there are several options you would see here. And for the DUT type, DUT system is the standard power AP, and another one is it's a standard power AP, but with the support of proxy. So that's what you would see from the dropdown. And these are the elements, as you see, Tevfik covered in the DUT compliance test plan. So there are several options that how the implementation can be done. So in this case, the first option is that talking about if the DUT needs a BSS configuration to be supplied by the harness to be able to operate once it gets the maximum permissible power limits. So it is again implementation specific. So the DUT can on its own have that configuration and then start beaconing per se once it gets the response. If in case if it needs to be supplied, like maybe the default SSID or the passphrase, then the test harness can provide. Then, of course, we have another option is for to account the composite devices that supports low power and then also standard power devices. This is needed to ensure that those devices that supports LPA operation are allowed to operate before they get inquiry response from the test harness. And if the device does not support LPA operation, then they are not supposed to transmit. So based on this option, the test harness knows how to validate the behavior. And another option is this is for the DUTs that would need some mandatory information to be supplied for the test harness because we have seen implementations having either way, like they can generate the request or some devices would ask the DUT test harness to supply that information like a dummy FCC ID or the NRA information or rule set ID information so that it can populate the request and send it to the test harness to receive the response. And this is for the power cycle is like for the test cases 3.3 where there is a spectrum access update wherein the device sends a request and gets a response and then it's being asked to reboot. So upon reboot, it is expected that it can no longer use the previous responses. So for the test harness to know how long it should wait, so this is the user configurable because it depends on how long the device waits. If it's a standalone power device, it may be quick, but if it's a proxy or controller based implementation, it may take a little bit more time. So this is something providing flexibility for user to configure what is the time that it needs. And as far as RF test equipment, as we mentioned, it does supports 2 ways, automated as well as the manual. So currently we are using light point equipment for this demo, which supports fully automation of the verification of the RF measurements. And we also have an option for doing the manual measurements. So for the purpose of the demo, I would go with fully automated, and if time permits, we can also do one manual mode of execution. And we need to, the test harness needs to know the IP address of the RF equipment so that it can communicate and get the readings from the analyzer. And then this is for specific to the light point equipment using the port that is being used to measure. So with that, we can now I would go to the test cases, and in the test cases again we have several options here. And as I mentioned, so it's the optional for the DUT to support the inquiry request just based on a channel, frequency, or together. So that's where you see there is an option for the user to select based on the device support what all capabilities that user the device supports, and based on that the test cases would be populated. And you can use these options to expand the list, or basically toggle the list. And then this is to select and unselect all the test cases. Currently we have 29, but all of them are not mandatory. And I would say one of these 3, either frequency or channel, or channel and frequency, one of them is required. And then of course the server's validation test case that is mandatory for ensuring that the DUT does not connect to rogue AFC systems. So for the purpose of the demo, I would pick a test case, and then we can see the test execution. And on the right side, we have it would show on this panel on this pane the test execution. So let's get started. So since we have selected the manual DUT mode, so it does the harness prompts that. So one of the expectation from the test plan or the behavior is that we need to reset the device to its default, so that even if it has any previous responses from the harness, that it deletes that or erases those responses, so that it requests and acts on the new response that is being received. So I'm operating the DUT on a separate window, so you might see I'm moving the cursor in and out. Okay, so the DUT is being reset, so it's resetting. So it does take a couple of seconds to reset and come up. Yep. So it is reset. And then if you select so there are multiple options here, which will allow the user to, so let me set this URL, and then channel weight, and the certificate is, of course, it's present. So this is the configuration that we need to set, but it depends again on the implementation. I think if you set one time, it should probably retain for all the test cases, and then that should allow the user to proceed with the execution. So as I was showing here, this will enable the user to see the more information on the UI as the test running. And of course, all this information is being saved in the log files. So these options would allow DUT and tool if you select, so you can see the messages coming from the DUT as well as the tool. And then if you select those other options like debug, verbose, that will allow you to see the lot of debug information. that is being recorded as part of each step execution. So currently what is happening is, I think this would take at least 3 to 4 minutes this step to complete. The reason being is, as Tevfik mentioned in the test plan, before the device sends the inquiry request, we do measure across the Uni 5 and Uni 7, the RF test equipment measures in all those channels or all those bands and ensure that the transmission, if there is a transmission based on the DUT capability, if it is an LPI certified device, then it would check those limits are within LPI limits. And if the device is not certified, then it goes through all those Uni 5 and Uni 7 channels and then measures, and if it expects no transmission. And if there is a transmission from a standard power only device, then it would report as unexpected behavior. But that is something, as you see, the transmission is happening, and there is a lot of debug information which is being spit out by the RF test equipment, and it does measure in the width of 160, so that that helps to speed up the measurements. I think it might take another couple of seconds to finish the execution. So and there is other options here. You can keep this auto scroll, which will make the screen to move as you see the log messages. And there is also option to, if you once you understand how this execution happens, and if you have a specific messages that you want to look for as part of the execution, you can just use the search button to measure. To look for the strings that you want to see as part of this execution. And then we also have the upper part of the right that will show you as and when the test execution, let's say if sends a request, and then it will show the measurement variables. What we call is the deterministic of each step. So basically, you will see at each level. So yeah, I'll explain once we go through this step. So now it measured in those Uni 5, Uni 7 before it sends the request and ensure that there is no transmission. And now it's asking the DUT, okay, now you triggered the request. So let me send a request. Okay, I sent the request, and then should have already received the response. Okay, as you see, the request is being inquired on different channels because it's so quick that you can see the response also is being sent. And then it does, once the AP receives, in this case, the AFC DUT receives the response, then it chooses the mechanism, whatever the mechanism, ACS, or it could be again implementation specific, and then decides to pick a channel and start operating. So we would expect another pop-up asking for user to input the channel that is being used by the AP to operate in standard power mode, which will then be fed to the RF test equipment to measure that it is operating within the limits provided by the harness. So while that is taking place, because there is a 60 seconds wait, the reason, I'll explain why is that. So I see from the DUT, let me just check what the channel that is operating. See that it's operating at channel 65. And now that value is fed to the RF test equipment, and then that will use to determine the EIRP being used by the DUT to transmit. So while the RF test equipment is doing the measurement, so let me try to explain what are these that we see here. So this is the what we call the first step, where before the request is being sent, the RF test equipment measures that there is no transmission there is no standard power transmission because we have this device supports LPI operation. So there is no standard power operation, and that's the value set is false, means that there is no standard power operation is being observed. And then the test harness also checks that the request is being sent by the DUT. So it means the test harness has received the request, and it did indeed receive the request. That's why it's setting the true. And then, as I mentioned in the test harness scope, it does verify that the request is properly formatted, which means it is following the Wi-Fi LAN's AFC system to device specification, and then containing the mandatory information such as location, temporary FCC ID, and then uncertainty information. So it does have that information. That's why it's validated and say it's true. And then there is an inquiry response. So here, what it does is, so the request, the response is being sent because it's being sent by the harness, and then the AP starts operating. That's where we have input the channel 65, and then it measures the ARP and then ensures that it is following the limits provided by the AP, and those we can see it in the log files. And then because this device is supporting both channel and frequency, so in addition to the EIRP measurement, it also needs to do the adjacent channel emissions, so that the DUT is following the mask provided for the adjacent channel frequencies. So with that, let me just, I think there is several log files, but I can show you we have run one test case here, but in case if you run multiple test cases, we have this HTML file that shows the DUT type and then model and the name, and then of course this is the summary table that I was talking about, the test case name and then pass fail result, and then you see the each FCC requirements. Yeah, and then we have there is several log files that are being a user can refer to, and then it's just here. You can just go to the cloud reports. You can just go to any of these folders, and then you will see those information.
All right, Lakshmi. Well, this is really comprehensive and highly informative. I haven't seen this myself, so I really enjoyed your presentation. We have about 4 minutes left. There were lots of questions, lots of discussions, but the advantage of having so many experts on our webinar is that they were able to answer the questions as they came up, and I'm really grateful for that. So Lakshmi, we have about 3 minutes left. Let's go to your final set of slides, because they're I think would help bring it all together. So Lakshmi, please go ahead.
So now we are going to talk about the AFC DUT testing process for the FCC certification. So as you see in this slide, so there are two options that the SPD vendors can go through the certification. So this testing can be carried only by the FCC accredited test labs. So we do have, so option one is where the SPD vendor can go to FCC accredited test labs and complete this test plan and then submit the test report. Then that test report is evaluated by TCB, and then TCB provides the certification grant. The option two is the Wi-Fi Alliance members can go to FCC accredited and Wi-Fi Alliance recognized labs and do the testing and submit the test report to the TCB, and then TCB evaluates and provides the grant for the certification. And yeah, so the next steps is, again, Wi-Fi Alliance remains committed to enabling the 6 GHz standard power device ecosystem. And Wi-Fi Alliance will make this entire DUT package and the proceedings of this webinar publicly available, and we will share that link shortly. So the current status of the DUT packages is the STI specification 1.5 is published, which supports the protocol version 1.4. And then we have a DUT test plan 1.3.3 and 1.0.1 is being published, and they may be an update to the test vectors, but unlikely to a test plan. And we are working on the DUT test harness package, and which will have. So we are also receiving some feedback from the OET labs, and we are very glad that we have received such feedback. And one of the things that we are looking at is the randomization of the AFC mask. And then, of course, supporting the harness package, we will also be updating the guide, testing starting guide by early June. Okay, yep. Sorry, just ran, I think, a bit over time.
No problem, Lakshmi, and thanks again for the presentation. I also wanted to thank my other co-webinar participants. Excellent presentations from everyone. We only have about a minute left, so instead of answering questions, I will just share with you the plans. And of course, everyone on this webinar, as well as at Wi-Fi Alliance, is available for follow-up. If you're interested in the topic, please email us. Our plan is to inform all the registered participants when we post the webinar materials, that is the video from today's session, as well as the presentations. We will post those on the web very soon, and we will notify you when the materials are available. We cannot speak for FCC, but our plan is to provide all these materials once completed to FCC and hopefully enable and expedite approval of the standard power devices. So with that, we are at time. Hopefully, most of you got some benefit out of this. And if there is more interest, we can try to host another webinar such as this one and continue to make progress. So thank you, everyone, very much for dialing in, for participating. And I look forward to your follow-up questions as they come in, and we'll be in touch. So thank you and goodbye.